guys, and welcome to a new video. In this video we are going to solve this exercise taken from an exam. Actually, I already solved in my first video the first part of this exam, and in particular I solved question A, B and C. So all these points are already solved in my first video if you are interested. But and in this video we are going to solve point D and point E. So if you are interested you can watch my first video, but in any case I'm going to sum up briefly the results of these first three points of the exam. So in this exam there is basically a thin metallic ring whose mass is 4 kilograms and the radius is 50 centimeters. It is free to rotate in a vertical plane about the center O, and it is connected to point O by a thin rigid metallic rod, and the mass and the length of the rod is M and R respectively. Okay, so here in the first question we are asked to determine the moment of inertia I of the system with respect to the point O. So here basically we already solved this first point, but the idea in point A is to sum the basically the moment of inertia of the rod and the moment of inertia of the ring with respect to point O. And here we basically obtained mr squared plus 1 over 3 mr squared for the rod, so the sum is 4 over 3 mr squared, which is, if you put in the values for m and r, the total moment of inertia is 1.33, and this is kilograms per meter squared. Okay, so kilograms times meter squared. So this is the first question. The second point is about the frequency of small oscillations around the equilibrium position, and this is important that the oscillations are small and around the equilibrium position. And in this second point you have basically to consider the frequency of the system, which is omega over 2 pi. Okay, but here omega is basically given by if you watch the video I explain where this omega comes from, and basically omega is linked to the radius of the ring. So here the result is 1 over 2 pi and omega is 3g over 8r, all under square root. Okay, and if you put in the value for g and r, you should obtain 0.43 Hz. Okay, so and in the second point here we basically resorted to the fact that the oscillations are small, so you can use the fact that the sign of theta is basically theta. Okay, so as far as the third point is concerned, here we have to find the angle theta 0 by which the rod is rotating presence of this mass. So in the third point we have to consider the mass m here, and here basically we already found that theta 0 is pi over 6, which is 30 degrees if you want. Okay, and you can find this theta 0 considering the equation of motion, the equations of motion of the system, and considering that here the text says at equilibrium, so you basically have to put the sum of the forces equal to 0, and from here you basically find theta 0. Okay, but now in this video I want to focus on the question D and question E. Okay, so these are the result from the three first points, but in question D we are asked to focus on the potential energy of the system. So plot the variation of the system's potential energy, including the suspended mass, as a function of the angle. Okay, so here basically we have the ring, the rod, the string, and the mass m. We already know the moment of inertia of this system. We already know the frequency of small oscillations of this system around the equilibrium position, and in the third point we already determined the angle theta 0 at equilibrium, for which this mass is at equilibrium. So for the system potential energy we have to basically consider the potential energy, let's call it U, given by the potential energy of the mass m. So we can call it maybe um plus U, which is the potential energy of the system made up of the rod and the ring. So here maybe we can write U rod plus ring. Okay, so this is the total energy of the system, and we have to keep in mind that the energy of the system is defined up to a constant. So this is important because if we want to determine the potential energy of the mass m, we know that m basically can move along this axis z, but we can express basically the coordinate of m with respect to z as a function of theta, because we know that um is basically mgh, where we have the mass g and the eighth of the mass m, and here we should basically also write plus a constant, because we know that the potential energy is defined up to a constant. So here this h can be expressed as a function of z, which is actually given by r times theta, because we know that for a change of theta, of the angle theta, we have a change of the position of m, which is theta times the radius of the ring, and we have also to add minus here, because we know that if theta increases, we know that z goes down. Okay, so we need this minus, and here we should also write plus a constant cancel this constant, which will be this constant, because we know that the potential energy is defined up to a constant. So the potential energy for the mass is just m minus m g r theta. Okay, and as far as now we have to determine also this potential energy. We know that also this potential energy for the rod is a function of theta, because we know that if the rod is if the radius is like this, is vertical, we can say that the potential energy is 0, and if the ring is rotated by an angle theta, we know that the center of the rod is basically here, which is a distance that we can determine, because the distance again can be determined considering h, and this time h. Okay, so here obviously the mass is in this case m, and then we have g, and then the h, and the h can be determined considering just r over 2 minus r over 2 cosine of theta, because we know that if this is the position in which the potential energy is 0, this is a general position, we have to consider this distance. So this distance here, which is given by r over 2 minus this distance, which is r over 2 times cosine of theta. So this is the result for h. So because of this we can write that the potential energy for the rod is just m g r over 2, and then we can write 1 minus cosine of theta. Okay, so this means that the potential energy of the system is a function of theta, which is minus mg r theta plus mg r over 2 times 1 minus cosine of theta, as we said. Okay, so potential energy of the mass, potential energy of the rod, and we have to plot the this function as a function of theta, but here probably is more convenient to consider this function, which is the potential energy divided by mgr. Okay, we know that m, so this m is m over 4, so because of this we obtain that this u of theta is 1/2 times 1 minus cosine of theta minus theta over 4. Okay, and this function is actually not so easy to plot. We know that the minima of the function u is in theta equal to theta 0 plus or minus 2 pi times k, where k is an integer number and theta 0 again is pi over 6, as we said, and the maxima of this function are in theta, are for theta equal to 5 pi over 6 plus 2 pi k plus or minus 2 pi k. Okay, and here I have the plot of the function, which is this one basically. As you can see, we have here the minima useful for the next question. Okay, so this was question D, and we determined the potential energy of the system. Now let's move on to question E. Here for question E, we basically have to find the equation of motion of the ring and rod system, again for small oscillations about the equilibrium angle theta 0, and we have also to find the oscillation frequency. And here we have also the postapheresis formula for sine of theta minus sine of theta 0. Okay, here for this question actually there are two different methods. Let's see the first method for question, this was question E. Okay, so the first method is basically a standard method in which we have to consider the equations of motion for the system. So we know that for mass m we have the tension of the string, and then we have obviously the weight of the mass m. So we can write that m times the acceleration, which is z, the derived and the second order derivative of z with respect to time, and then we have t minus mg, so tension minus weight. Okay, so we have to write down the equations of motion for the system. This is the first equation for the mass m, and we know that the acceleration for m can be written as minus r times theta and the second order derivative of theta with respect to time. Here basically we are saying that the acceleration in the z direction is given by this product where we have the angular acceleration. Okay, so the second equation that we have to consider is the equation of motion for the rod, and as we did in the first point, we basically have to consider the angular, the moment of inertia times the angular acceleration for the system, and this is equal to the sum of the momenta with respect to the point O. So here we basically have two momenta, t times r, and then we have minus m g r over 2, and then we have times sine of theta. Okay, so these are the two equations in a system that we have to consider, and then now we have to consider also this substitution. So I'm just going to copy and paste this equation, and then I'm going to write, instead of the acceleration, the linear acceleration, instead of the linear acceleration I'm going to write down minus r and then the angular acceleration. Okay, so here maybe it is convenient also to multiply by the radius. So here, as I said, we have this one, then here maybe we have to also again multiply by the radius. So again I'm going to duplicate this system. Okay, so if we multiply, we have r squared here, and then we have t times r as we have here, and we have also minus m r, and then we have g. Okay, So now if we subtract these two equations, we will get minus m r squared, and then we have minus I that multiply the angular acceleration, and then we have 0, and then minus mgr plus mgr over 2 sine of theta. Okay, so we have basically to find the angular acceleration, so let's move on. We can change the sign, so we get this okay, so now again we have to find this value, so I'm going to divide by this term, so we end up with mgr minus mgr over 2 sine of theta, and then we have mr squared plus I. Okay, so here we can also write here, for example, we can consider gr, okay, and we also know that m is m over 4, so we can write mgr, and then here maybe it's better to do so, okay, and then we can also take these two, so we end up with 2 times I plus mr squared, okay, 2m over m, okay, because we have this m from this first term, and 2 and m, which is this m and this 2, and then we have also minus just the sine of theta, okay, because we have mgr, which is mgr, and this 2, which is this 2, so we end up with just the sine of theta minus sine of theta. Okay, so now we can also change again the sign of in this parenthesis, so we end up with minus mgr over 2I plus mr squared, so we change the sign, so we end up with this one. Okay, so we end up with this one, and we know that this is just the sign of theta 0, which we demonstrated in the first point in the first video. So this means that here we can write a difference between two signs, so sine of theta minus sine of theta 0. Now that the text says that we have to consider small oscillations about the equilibrium angle theta 0. So this basically means that our angle the angle theta is close to theta 0. Okay, so this means that for example cosine of this will be just the cosine of theta 0, because theta and theta 0 are basically the same, and this difference goes to 0, so we can use the approximation for small angles. So that means that the angular acceleration will be minus mgr over 2I plus mr squared, and as we said, we have again 2, then we have cosine of theta 0 times the angle here, because theta minus theta 0 goes to 0, so the angle is theta minus theta 0 over 2. Okay, so we can cancel these 2, and then we end up with theta, which will be minus mgr cosine of theta 0, and cosine of theta 0 is a known value, and then we have theta minus theta 0, and we know that cosine of theta 0 is 3 over square root, so we can write just 3 over square root mgr. Okay, so this is the final result. Let's realize that cosine of theta 0 is actually 3 under square root over 4 over 2, so here we end up with 4. Okay, so this is the final result, and this is basically a harmonic equation where here we have omega squared, so we know that the frequency, we have to find the frequency, will be omega over 2 pi, so that means that we end up with 1 over 2 pi, and then we have this result under square root. Okay, so this is the final result of the question, and if you put in the value of all these values, you should end up with 0.37